Hi everyone, here is your video on volumes by cross-section. So we've been spending several days in class doing volumes of revolution. That's whenever you take a 2D area and you revolve it around a line, either an x-axis, so like in this case it was the x-axis, or another random line like y equals -2, or even another line, a vertical line. We did some of these where we rotated around a vertical line like x equals -1. Either way, in these cases, whenever you take your shaded area and you rotate it, whatever that area may be, whenever you rotate it, the volume you create, if you were to chop it up, you would end up with circular cross sections. So in this case, you could either have a disc, like a tortilla, or a washer, like a donut or a Cheerio. Down here's another example of a washer. And there were two ways that we could chop these things up. You could imagine a knife that was, whoa, that's the sharp edge of the knife. You could imagine chopping like vertically like this, where you get a bunch of circles. I remember we added up infinitely many cylinders and they're infinitesimally thin. Like they're basically two-dimensional. They're so thin, but they're technically little volumes. And we added up infinitely many volumes to get the whole volume. In this case, you do the area, or I should say the volume of the outer cylinder minus the volume of the inner cylinder. And that estimated this volume here, not the hollow part, but the actual outside here. And then this one here, we took this area and we rotated around x equals -1. Again, if you took your knife this time, there's a sharp part, here's your handle, and you chop this way, horizontally. This is chopping horizontally. The other ones we chopped vertically, okay? So in this case, you still have circles, or cylinders, I guess, going from the bottom up to the top. So those are what we've already done, circular cross sections, okay? But not every single volume is going to have a circular cross section. And I showed you a couple videos in class about what that would look like if they were not circular cross sections. I'm just going to show you those now. So what if you had a volume and if you were to chop it up and you pulled out random slices, what if they were semicircles, or in this case, squares, or right triangles, or rectangles? Here, you're chopping it up into a bunch of semicircles. We'll do a semicircle problem. And here we have triangles. So it kind of looks like a slug on the paper if you were to look at this 3D shape. You're going to be building these using this sheet right here. Obviously, you're not going to do as many random cross sections as on here, because this is like, I haven't counted them, but it's like more than 20 cross sections, and you're not going to do that because these are like full-blown projects and you're just doing it as like a quick visual. So you're going to do 3 semicircles and then 3 squares and then 3 triangles on your notebook. I'll show you a quick video of how to do that, so don't worry about that quite yet. Okay, so jot this down for yourself here. Like we said before, some 3D objects do not have circular cross sections when you slice them up. They can have different shapes. They have to be similar. So they either all have to be triangles or all squares, all semicircles. Like whatever shape you have to have the same shape throughout in order to use the method we're going to be using, okay? And they're all similar to each other. They're not congruent, but they're similar, okay? All right, so a typical AP exam question will sound something like this. So why don't you jot this down? And we're going to use the same exact base for all of these, but we're going to do 3 different cross-sectional shapes: a semicircle, a square, and a right isosceles triangle. Okay, so right here, this is the problem we're going to consider. What if we have finding the volume of the solid whose base is a region R and whose cross-sections cut by planes perpendicular to the x-axis are semicircles. The region R is created by root x, y equals 0, x equals 2. So, wow, we just got a lot of information there. Let's go ahead and do a sketch of what is happening here and kind of break this down a little bit. All right, first thing is we have the square root of x. We did a lot of square root of x already with volumes of revolution. So this one should be similar or familiar. We're starting at x equals 0, and we're ending this time when x is 2. And for the first one that you're going to build, the semicircles, they're going to be perpendicular to the x-axis. So this is a thing that sometimes people mess up because they're just reading too quickly. Picture your x-axis. This is obviously your x-axis. And then I want you to try and lay your pencil on your paper so it's perpendicular to the x-axis. Like, what would that look like? Hopefully you're holding your pencil like this, okay? Or like this. This is perpendicular to the x-axis, okay? You can also be perpendicular to the y-axis. That would look something more like chopping it this way. And we're gonna do one like that, but right now we're perpendicular to the x-axis. The reason my region stops here is because I'm stopping it at x equals 2 and y equals 0. So this is the line y equals 0. But anyway, I'm chopping this thing up. And what they're telling us here is that cross sections cut by, when you cut this thing up perpendicular to the x-axis, the cross sections are semicircles. So what it's going to look like is what you're going to build in the video that I'm going to show you. Actually, let me show you that video right now, just so you can get an idea of what's happening. I'm going to show you a video in a video here. So you might have to turn up the volume a little bit to hear this. Let's see what happens. Here we go. This is, again, going to show you how to build. So you need scissors, you need tape and or glue, and your notebook. Hey, here's a quick video on how to make your volumes. So you should have one of these. It should be on colorful cardstock paper. It's on Google Classroom if you lost yours, so you can print it out. All right, so your three shapes here. You have semicircles, squares, and isosceles triangles. There's a little issue with the printing. There's little tabs on your circles, semicircles, which is good. The squares and right triangles don't have a tab, so you're gonna have to, you have to make your own tab whenever you cut these out. Whenever you make your semicircles, so ideally these are gonna be on 3 different pages in your notebook. I know some of you like to cram everything together. Try to just spread out your work a little bit so you can organize all the calculus we're gonna be doing for each problem. Okay, so here's square root of x. Draw it so it takes up I don't know, 5 or 6 lines in your notebook. And are you ready for this? You have to cut out, there's 3 of them for a reason. You're gonna cut out 3, but make them different sizes. So closest to the origin, I used I don't know, a couple. Sorry, it's kind of hard to do this facing the camera. But anyway, cut out the circles, semicircles. I should re-record this, but I'm not going to. I did 1 circle, and then I did 2. No, I did 1.5 there and 2. But anyway, you're taping them vertically, okay? And notice the little tab is keeping them so they're going to be upright whenever you keep them up. Again, you can cut more of them out if you want a better visual, but I feel 3 is enough to get the idea of what's happening. All right, just real quick, whenever you do it again, so you're going to redraw the square root base again. This time, this is critical. Your squares are getting cut horizontally. So here's your notebook. You're going to go chop this way. So don't mess this up. They should be running along this way, okay? So again, the squares are going to be different sizes. I went from, I don't know, 2 squares to 4 to 5. Feel free to cut them so they fit from 1, they should go from here all the way till you hit the curve, okay? And then this one here, draw one more time, and you're gonna tape one more time with right triangles. They're isosceles. There we go. This is a good view. So you can see my triangles get slightly bigger as you go. And one thing that will help, okay, I didn't do it on this one. I didn't tape down on the other side. See how it's kind of not anchored down all the way? You're gonna take tape and you're gonna tape down the other side of it. So you have tape on each side. You'll see what I mean when you do it. You just want the squares or the rectangles to be standing up whenever you put them up like this. But anyway, have fun, take your time, and whenever you're done, continue the video. All right, so you can start doing the semicircle one. Don't worry about the square and the triangle one until we're ready for that. I do want to show you a visual before we do any actual math. Now, I realize that the base here is a triangle, and our base is not a triangle. Our base is this square root of x shape, but it's just a visual. And we're chopping ours vertically, and this one, unfortunately, Calculus and Motion doesn't have that one. They have semicircles where you're chopping horizontally, but it's okay. Again, it's just for the visual. So here's what's going to look like. So we have our base. In this case, it's a triangle. You're going to chop either horizontally or vertically. And I'm going to drop this flat, as it says, so you can actually see it a little better. You're imagining that the base is flat on your paper. And what you're going to do is imagine shapes coming out of the paper. So in this case, you're imagining a bunch of semicircles. And notice the diameter is getting larger as the distance here gets larger. So let's sweep one semicircle. Again, notice the diameter gets smaller here as the y-axis and this distance get closer together. And let's make a solid out of this. So remember, you're making a 3D solid. Keep that in mind. So this looks like half of an ice cream cone, I guess. And there's what it looks like. Oops. Come on. Woo. All right. So remember, this thing is actually like perpendicular to the x-axis when you chop this up. No, it's perpendicular to the y-axis when you chop it up, but we have it flat so you can actually see it a little bit better. All right, so that's what's happening here. Let's go back to this problem. Whenever you do a problem like this, there's a few things that you need to think about whenever you're about to set up and figure out like how you're going to do this. First thing you have to think about is like, how are you going to slice it to get your cross sections? Are you going to do it horizontally, which would be like this way, or are you going to do it vertically, which is how we're doing it in this case? So in this case, we are vertically up and down like that. You're going to go chop, 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 all the way from one side to the other. And then you're going to add up infinitely many of those shapes. It's just instead of adding infinitely many circles, you're going to add infinitely many, well, in this case, semicircles. Where do the shapes start and where do they end? In this case, we're chopping from 0 to 2. That's going to tell you the limits on your integral or the bounds of your integral. So in this case, it would be like from x equals 0 to x equals 2. Another thing, in order to get a needed edge of your shape, do you subtract x values or y values? So think about the video distance between 2 points. In this case, so here's a random edge of my semicircle. I'm going to try and make it look three-dimensional. It's not going to look very good, but like here's an example of a semicircle coming out of my paper. If I got closer to the origin, it'd be smaller. And I could make it even smaller. So again, this is like what's happening here. And this is what you're taping down on your paper, little pieces like that. So if you want the distance of a vertical line, you subtract y values, top minus bottom. So y values in this case. And then what's the area of one general shape? Or I guess it's volume, but let's just think area. And then we'll just put a dx or a dy at the end of it. So anyway, because remember, you're finding the area of one random shape, and then you're going to add up infinitely many of them. Just like before, you added up infinitely many circles. Very similar to volumes of revolutions. We just don't have pi r squared. We have different areas. Okay, so the video already showed you how to build this. Let's get started. So in your notebook, hopefully you have, I would pause if you haven't made your semicircle one yet. You want, again, something like this going on, having 3 circles coming out. All right, let's get going. Okay, so you have this taped down in your notebook. It might be helpful to do another quick sketch here. You can kind of decide if this is helpful or not. Again, you don't have to redraw because you just built it. But anyway, here's the sample edge. And when I say edge, you have to get used to drawing a line going up and down or a line going, across. So in this case, here's the edge of a random semicircle cross section. And this is the process you're going to go through. So follow along here. I need to find the diameter of my semicircle here. So the diameter goes from the top to the bottom. So what I'm going to do here is top minus bottom. I'm subtracting my y values here. So, all right, what's the y value up here? This is changing. Like my diameter is getting larger and larger as I go. So I can't just put a number here. That y value is square root of x because it's on the curve square root of x minus the y value down here is always 0. Whoops. So I'm going to have square root of x minus 0. So square root of x. All right, so diameter would be the square root of x. That's what I just found here. Okay, but like I'm adding semicircles, and you have to remember the area of a semicircle. Well, a whole circle is pi r squared. A semicircle is half of that. So it's pi r squared. You can either do over 2 or you can do like 1/2 pi r squared. I'll do pi r squared over 2. which again is the same as 1/2 pi r squared. So I really need radius here. Well, radius is half of diameter. So if diameter is square root of x, then the radius is going to be square root of x over 2. So always start by finding the edge length, the edge of your shape. Then you're going to go ahead and find the area. So first get an edge, then find the area of one general shape. So here's my general formula. And then I have pi r squared over 2, or 1/2 pi r squared. I'm going to fill in what my radius is. So pi r squared over 2. Notice it's over 2 again because like this is my radius and this is cutting the whole area in half to get a semicircle. Okay, so let's simplify this a little bit before I think about an integral. So I'm still just doing geometry right now. So square root of x over 2 squared would be x over 4 over 2. And let's break this down a little bit. This would be pi x over 4. Dividing by 2 is the same as multiplying by 1/2. So this is pi x over 8. And remember, this is the area of one random semicircle. Okay, so how many semicircles do I want? I want infinitely many. I want to add up infinitely many semicircles. How do I add up infinitely many things? You're going to use an integral. So my shapes, where do my shapes start again? They started here at x equals 0. They end here at x equals 2. Whoop. And okay, I'm going to sum up the areas of infinite shapes. Now I have area in parentheses for a reason. I'll tell you that in 1 second here. Okay, so I go from x equals 0 to x equals 2. And really all I'm going to do is add up infinitely many areas. So whatever was right here. Oh man, what the heck? All right, I don't know what just happened. What the heck? Okay, I'm adding up infinitely many of these. So that's going to go right here. And if I just put pi x over 8, that is an area. But I really want it to be a volume, so I'm going to put dx at the end to represent the tiny, tiny width. All right, so let's just do a quick antiderivative here. Don't ever forget your antiderivative skills. I'm going to take out the constant, so then it's just x dx. And then an antiderivative of x is x squared over 2. Vertical bar notation, people, from 0 to 2. So then I have pi x squared over 16 from 0 to 2. So then that'd be pi times 2 squared over 16 minus pi times 0. That goes away. So I have 4 pi over 16, which is pi over 4. All right, cool. So again, this right here is area. And then whenever you put a dx at the end, that makes it a volume. Keep that in mind. All right, I'm going to stop the video here and pick up at another one. Just so you know, the next one is going to pick up, right here with the square. We're going to do that one next. So start building that one and then come back for the next one.